Hi, so this is a recap of the photoelectric effect. Complete warning, I haven't fully taught this for quite a few years. Generally, when I do this now, it's for revision, and I'm going in cold because why not? I'll probably have to start again at some point, but it's a bit of a challenge and it's good to challenge yourself. So the photoelectric effect, we need to start by thinking about a metal. So I'm going to draw a metal, and in that metal, there are lots of metal ions, positive ions, and they are surrounded by a sea of delocalized electrons. And I'm only going to draw the electrons because life is short. Okay, so we've got a sea of delocalized electrons. So there's lots of electrons that are free to move, as it were, in a metal. Now, what we find is that if we emit some light, or project, that's the word, project some light onto this metal plate, what we sometimes find is that these electrons escape. And that's the photoelectric effect. You add some light to the metal plate and the electron is ejected. The weird thing though, is this only seems to happen for UV light or sometimes very high frequency visible light. So maybe violet light or blue light. And that depends on which metal you're looking at. But for most metals, this only happens if there's UV light incident, that's the word, incident on the metal. Now, why is this? This is the start of quantum mechanics, and it's starting to explain how light can behave as both a wave and here as a particle. So I want to think about these electrons, okay? These electrons are stuck inside this metal, and they have something, the metal has something called the work function, which is phi, and the work function is that's how I've written function, you should write it as a real word, is the energy required to emit an electron from the surface of the metal. So if we can somehow give this electron enough energy, it could be emitted from the surface of the metal. And in my little example, I'm going to do my example in pink. I'm going to say that phi equals 6. I'm not giving it a unit because it definitely isn't 6 joules. It's probably more about electron volts, but this is just to help. Okay, so I'm going to say that phi is 6. Now, let's say that our UV light gives the electron an energy of 10, okay? And if this UV light gives one electron an energy of 10, that means that they've used 6 of it up to get out of the metal. That's what the work function is. So out of that 10 energy, 6 will be used to get out of the work function. I'm going to draw it on this one here because it's going to obviously go to this electron here, let's say. And that means that there's 10 minus 6, which equals 4, left over. So 4 bits of energy left over. And that left over is going to be the maximum of the Ke of the electron. So the electron is ejected out of the metal, and any energy that it was given by the light that's left over once you've taken the work function out of the way goes to the kinetic energy of the electron. But we write Ke max because if, say, instead of this electron here, we want to make this electron escape, this electron needs more energy to escape because it's not at the surface. So this electron is going to need phi plus a bit more. So let's say the light gives this electron 10 as well. It's going to have 6 for the work function, and maybe to get to the surface here, it needs another 2. So 6 plus 2, and then whatever's left over, so 10, what we get from the light, the energy from the light, is equal to 6 plus 2 plus 2. And this 2 is the kinetic energy that this electron would have. So if both of these electrons are hit by the same amount of light, they're both given 10 units of energy. Because this electron is closer to the surface, it's going to get more kinetic energy than this electron because they both need 6 to escape the metal, but this electron also needs some energy to get to the surface of the metal. And this is all a very long-winded way of me trying to explain the photoelectric effect equation. And that is that E equals phi plus Ke max. Now, all of these are energies, so they're all in joules. The energy from the light is equal to the work function plus the kinetic energy maximum, and they're all in joules. But a big thing that I'm really missing here is this idea of the energy of the light. Now, this, like I said, the photoelectric effect is the start of quantum mechanics, and it helps us to think whether light is a wave or a particle. And the photoelectric effect proves that light can act, or does act here, as a particle. Now, why is that the case? That's the case because this doesn't always happen, okay? The reason we know the photoelectric effect proves that light can act as a particle, I'm going to write particle model evidence, is because this only happens, I don't know why I've written the arrow there, this only happens when a high enough frequency of light is used, e.g. UV. It rarely happens for normal light. It does sometimes, but rarely, and pretty much never happens for infrared. And increasing the frequency of light increases the Ke max, and we'll talk about why that is in a moment. And we also find that increasing the intensity of light, that increases the rate of electron emission if you can't see that there, sorry, if this light has a high enough frequency to emit electrons. If I used infrared light, nothing would happen. So let's try and draw that out actually. So I'm going to draw the surface here once again. And I'm going to have lots of E's, lots of electrons that are ready to go. And I'm going to think about I used the right colour there actually. I'm going to think about what colour of light I might use. So I normally don't have a red pen, but I do have a pink pen. So if red light, here shown as red and pink light, comes in, there's no emission. Okay. If, let's say, blue light came in, if it was a metal with a low enough work function, I'd get electrons emitted with the blue light. And if the blue light works, and then I add in purple light, or even better UV light, I'd find that electrons are emitted and that they would have a higher max Ke. Now, if I increased the intensity of the light, let's actually write intensity. If I increase the intensity of the light for all three of these, if I increase the intensity of the red light, there'd still be no emission. If I increase the intensity of the blue or the purple or UV light, both of these would find the same thing. You'd find that there are more electrons emitted per second, but no change in max Ke. And that would be the same for both the blue and the purple light. Now, the only way we can explain this is if we think of light as a particle. And we have this idea that light acts as a particle, and that particle is known as a photon. A photon is a packet or a quanta, which means a little bit, of light. And we often draw them like this. Imagine you've got a wave and you split them up into little bits. The little bits are the photons, the quanta of light. Now, each photon has an energy equal to hf. So E is the energy of the photon. H is something called Planck's constant. And Planck is somebody who came up with a lot of stuff about quantum mechanics. And F is the frequency of the photon. So what we can work out from this, because H is a Planck's constant, we can say that the energy of the photon is proportional to frequency. So that means if we think about our colours of light, our red light has got low energy photons because red light, or pink as it is here, is low frequency light. It's low frequency and long wavelength, sorry. And then as we move up to purple, we're getting to higher energy photons because purple and UV have got a high frequency. Now what's happening is, I'm going to draw it another time. It's going to keep happening. Here are my electrons. And this time I'm going to draw some at different levels. Okay. Now remember, this metal has got a work function phi. And I'm going to now draw a photon of light. Okay. Really important. One photon can interact, I've missed out the end, can interact with one electron. It's a one-to-one interaction, super important. And the photon gives all its energy to the electron. There's no halves, there's no sharing. The photon gives all of the energy to the electron. So let's go back to our original values, as it were. We gave a value for the work function of 6, I said. And I said that the light had an energy of 10. So if an electron at the surface, this electron here, okay, absorbs this photon, it absorbs 10 units of energy. It's going to use 6 of those to escape the metal because it's at the surface, which means it has 4 left for Ke. If instead I have another photon with 10 again, I'll do it in green this time, but instead it decides to be absorbed by this electron here, this electron will be ejected from the surface, hopefully, but it's going to be ejected from the surface with less. So it's going to take 6 to escape the surface, but before that, maybe it takes 3 units to get to the surface. So then it's had 10 units of energy, it's taken 3 to get to the surface, it takes 6 to escape the surface, so this would only have 1 unit of Ke. Now the interesting bit comes if I just extend this over. What if I don't use purple light? What if I go back and I use my red light, which is pink, as we know, okay? Now this red light, because E equals HF, and red light has a lower frequency than purple light or UV light, this red light is going to have less energy. So let's say that this red light has 5 units of energy per photon. Now the work function is 6. So if this electron captures this photon with 5 units of energy, it still hasn't got enough to get out. And what doesn't happen is it doesn't go, oh, well, I've got 5 now, so I'll just wait for another one. And when I get another one, I'll have 10 so I can leave. It doesn't work that way. Once it's taken that energy, if it's not enough, the energy gets discarded. So this is why low frequency light or low energy photons can't work for the photoelectric effect. They can't eject the electrons because the energy is used in a one-to-one interaction. So let's think back to this equation, E equals HF. E, and also we had E equals phi plus Ke max. We often put these together and we say that HF equals phi plus KE max, where HF is the energy of the photon, phi is the work function, and KE max is the maximum energy that the electron, the photoelectron, we call these emitted electrons photoelectrons, will have. Now, there's something clearly here about when will this start to work. So if an electron has the right amount of energy exactly to if a photon has exactly the right amount of energy to let an electron escape, so let's say I had a photon of, I'm going to go green light that had 6 units of energy here, then an electron that it hit at the surface would be able to just escape, but it would have no KE. Now we call this event when we have the threshold frequency. So the threshold frequency is the frequency of light that just allows electrons to escape the surface of the metal. And then there is 0 KE. And if there's 0 KE, that means that if we think about E equals HF equals phi plus KE max, well, if there's 0 KE, what I can do is cross out that because it's 0, and I'm going to just add a little naught here. HF naught equals phi is another equation to know. The work function equals HF naught, and F naught is the threshold frequency. So this is proof that light can act as a particle. I want to think about what increasing the frequency does. So let's do that. Let's do blue. So not increasing the frequency, sorry. I want to think about what increasing the intensity does. Now, increasing intensity means more photons are emitted per second. Now, because the interaction between photons and electrons are a one-to-one interaction, if there are more photons being produced per second, that means that more electrons can then escape per second. So more electrons can absorb, no, that's a B and S wrong around. More electrons can absorb photons per second, and therefore more electrons can escape per second. But this only works if the frequency is above the threshold frequency. If I had red light, no matter how many photons I throw at it, I'm never going to let those electrons escape. This only works if the frequency of the photons is above the threshold frequency, which means the photons have more energy than the work function, which means the electrons can escape. Now, this is a long topic, I'm not going to lie. The next that we need to think about is why does this prove that light is a particle? Why is it showing that light isn't acting as a wave at this point? Well, we need to think about what would happen if this worked for light as a wave. Okay, so I'm going to draw the same diagram. It's going to keep happening. Okay, so here's my electrons. Once again, I'm going to give a work function, and we're going to keep with the number 6. The work function is 6 units, 6 electron volts, 6 joules. It wouldn't be 6 joules, but 6 units. And let's say I've got some very, very low intensity red light, which is once again going to look pink. And if light was a wave, let's say that this red light was giving off had a power of 2 watts, which would be 2 joules per second, or 2 units, I should say, because I'm not using energies. So 2 energies per second. And let's imagine that this electron here is picking up those energies. If light was acting as a wave at this point, what we'd see happen is that this electron would start to basically fill up its bank. So in the first 2 seconds, in the first second, it would get 2 units of energy. In the next second, it would get another 2. And in the next second, it would get another 2. So after 3 seconds, that electron would escape. Because if I'm getting 2 watts or 2 units per second, then it's going to take me 3 seconds to get to the work function, and then I can escape. This electron down here would take a little bit longer because they're going to need to get enough energy to get to the surface and then escape. And what we would find is if we increase the intensity of the light, no matter what colour it was, let's say I keep it as red, but I make it more intense, that means there's more energy per second. So let's say that instead, when I increase the intensity, I get 3 units. I'm going to just write units per second. It would now only take the electron 2 seconds to escape. So I would always see a delay between the light hitting the surface and the electrons escaping, but the higher the intensity, the quicker they would escape. And it would work for any frequency of light given long enough. Now we don't see that happen. And the fact that we don't see that happen means that this is not going to work. This is not an explanation of light as a wave. The fact that what we do see happens means that it must be acting as a particle. And this is very important to think about, is that it's something called wave-particle duality. And it's that sometimes light acts as a wave, for example, refraction. That's very much a wave property. Interference only works if light is a wave. But sometimes it acts as a particle. And the evidence for that is the photoelectric effect, and also spectra, which we're going to look at in another video, so feel free to go and have a look at that one. Now, this wasn't hard enough, was it? So what we're going to do now is make it even harder and think about something called a photocell. Oh no, we're not. We're going to come back to the photocell in a second, because I want to go back to this equation one more time. So I'm going to go back to HF equals phi plus KE max. And we're going to think about what happens when you plot a graph of frequency versus max KE. Yeah, I think that's it. This is what happens when I don't look things up in time, and it's been a long time since I have taught this properly. So I am going to check it because I don't want to make a mistake. I've already spent 22 minutes on this video. I don't want to spend doing all that again. But you know, this shows you that you need to keep revising to keep learning. I was right. Okay. What we saw in this little example here, was it this one here? No, it wasn't. It was this one here. Sorry. This example here is what we did is we increased the frequency. Okay. And as we increased the frequency, we also saw that the KE maximum increased. So as we increase frequency, we also increase the max KE. So this is the dependent variable, the maximum KE, and the frequency is the independent variable, because that's what we can change. We can change the colour of light we're putting onto the surface. So if I plot a graph of max KE, that's going to be in joules, against frequency, which will be in hertz, I will get this shape of graph. Now I'm drawing this as a dotted line because I can't have negative max KE. So there we are. Now, there's lots of parts that we can always think about of a graph. We can think about the gradient of the graph, M. We can think about the y-intercept of the graph. And we can think about the x-intercept of the graph. And what we need to do is be able to work out what those things actually mean. And we're going to use this equation to help us. Okay. Now I'm going to try and get the equation HF equals phi plus KE max into the format y equals mx plus c. Now y here is KE max and x here is frequency. So I'm going to write KE max equals, now I need to get phi on the other side to make it so KE max is on its own, and it's going to become a minus phi because I'm moving it over, and HF must be in this little gap here, but no, I can keep it as it is. So F is going to stay there, and then I've got HF minus phi. It's the same thing, I've just moved the phi over. And what I can now do is I can compare the two equations. So Y and KE max, that's right, they equal each other. X and F is right, they equal each other. Which means that M and H must also equal each other, as must C and minus phi. So what I find is that the gradient M, don't know why I drew that line there, is equal to the Planck's constant, H. And I also find that the y-intercept, which is a negative, is equal to the minus work function. So if I want to know the work function, I just need to look at the y-intercept and minus it to get a positive number. If I want to know the gradient, the Planck's constant, I just need to work out the gradient. There's also one more thing to look at, and that's the X-intercept, and it must be a frequency because it's on the x-axis. And what we find is the X-intercept is the threshold frequency, F0. Now, the reason I wanted to go through that is because I look at this graph again slightly differently in a moment, because we're now going to move on to, we're on 26 minutes, the photoelectric cell, or a photocell. And this is not easy, I'm not going to lie. Okay, so a photocell uses the idea of the photoelectric effect to produce electricity, essentially. So what happens is I've got here a metal plate, and photons will be incident on that metal plate. And the photons, I've made them purple because they're UV, are going to release, let's draw my electrons in blue for now, electrons from the surface of that plate, and they are going to have KE that makes them travel towards this plate here. Now, if I then put this into a circuit, this can work as a battery. The KE of the electrons means they can travel around the circuit. But what I'm now going to do, just to make life a little bit worse, is add in a cell. And I'm going to add in the cell so it's in the opposite direction. And I want to make sure I get it the right way. So these are electrons. They're going to be repelled by a positive. So I'm going to do it this way around. And I'm really sorry if I do this the wrong way around. Like I say, don't teach this very often. But this explanation will be good enough. Okay. So what I've got here is I've got that the photocell is trying to make electrons travel this way. Yeah, I've knew it the wrong way around. It felt wrong. And that now looks like a capacitor, so that's great. Let's just start that again. I'm not starting the video again because it's going to take me forever. So this is the photocell. And I've got my photocell here. And I'm going to attach it to a battery. No, I've done it the wrong way around this time as well. So I start off with some photons. And when those photons hit this metal plate, they cause electrons to be emitted. Those electrons have got kinetic energy from the leftover energy from those photons, and they start to travel this way around the cell. Okay, so the electrons are traveling this way around the cell, but then they get to here, and this is the negative terminal of the cell. So this negative terminal of the cell is going to push them backwards. Now, I'm going to make this into a variable power supply. That's like a power pack, okay? And I'm going to start off with this variable power supply having 0 voltage. And I'm going to say that this photocell has a voltage of, let's say, 4 volts. At this point in time, when this variable power supply has no voltage, it's not opposing the photocell. So the photocell will be the only power source in the circuit, and the overall voltage of the circuit will equal 4 volts. But what's going to happen is I'm going to gradually increase the voltage of my power supply. Now, the photocell is trying to push the electrons this way, but my power supply is trying to push the electrons back this way. If the photocell has a voltage of 4 and the power supply has a voltage of 1, which one's going to win? Well, the photocell, because 4 is bigger than 1. But what I'm going to find is that the overall voltage of the circuit is now going to equal 3 volts, because I've got 4 volts pushing, but I've got 1 volt pushing back. It's a bit like forces. And I can keep increasing the voltage of the power supply, and I'm going to find that my overall voltage is going to keep decreasing until a very certain point. V equals 4 volts. And at this point, the overall voltage of the circuit is 0 volts. And that happens when the voltage of the power supply is equal to the voltage of the photocell. Can you see that? There we are. Now, why is that a thing? Why do we care about that? Well, this means we can work some stuff up about what's going on here, okay? Why does this voltage push back against these electrons? Well, these electrons, like I say, have been given, let's do a different colour pen, they've been given a kinetic energy. And what happens when I've got my power supply voltage equal to the cell of the photocell voltage is that KE is effectively wiped out. So at this point here, when the power supply equals the photocell supply, the KE is wasted, potentially. The electrons are slowed down. What we say is work is done against the electrons. Now, if you have done electric circuits, which you probably have done by the time you do this, you will hopefully remember that we can say voltage, the definition of voltage, is the work done per charge. So what we find is that the work done for a certain voltage equals QV. Now, Q, what we talk about here are electrons. The charge on an electron is E, and then the voltage is V. And at this point, when the power supply voltage equals the photocell voltage, what happens is that this work done, this E times V, it's not electron volts, it's E times V, is equal to the KE max, because this is the point where the work done completely uses up the maximum KE. Before then, there's still work done in these circumstances, but it's not done enough to completely wipe the KE. It's only when the power supply voltage equals the photocell voltage that KE max equals electron charge times the voltage, not electron volt. Now, why do I care about this? Because sometimes instead of seeing this graph here, you'll see this graph drawn a little bit differently. Instead of having maximum KE here, you will instead have EV here. If they're talking about the photocell, this will be EV, which is the work done against the KE max. And the reason this is useful is because this is measurable. I know that electron charge is 1.6 times 10 to the minus 19 coulombs, and I can measure that voltage with a voltmeter. I can't measure maximum KE. I can't catch an electron and see how quick it's going, but I can measure this. So in that circumstance, what you'll find is you have exactly the same equation, but before we had that HF equals phi plus KE max. Now we're going to replace KE max with HF equals phi plus EV. And you might get a slight variation, therefore, on your graph. You might find that instead of plotting KE max or EV, you might find that they plot instead just voltage against frequency. And this voltage is called the stopping potential, because it's the voltage that stops the electrons, that gets rid of the electron kinetic energy, the maximum kinetic energy. So if they do that instead, you'll get the same shape graph, but we need to think about how we rearrange this slightly differently. So now Y is just V and F is still X. So I'm going to think about Y equals mx plus c, but Y I want to be V on its own. So V on its own equals mx plus c. So I need to move phi over. So I'm still going to have hf minus phi, but because I should have EV equals hf minus phi, to get rid of that, I have E underneath them both. And in this circumstance, I'm going to write that h over E times f minus phi over E. So in this point, what I would find is that my y-intercept equals the minus work function divided by E, because I haven't drawn this very well. Let me just write equals mx plus c again above here, because then we can do this. Put some minus there. And that now the gradient equals h over E. You'll also find that this is still the threshold frequency. This is really, really hard. Okay, it's taken me 35 minutes to get to this point. But if you want to now have a go at some of the questions and read and watch the question video where I go through some of those answers, all of this theory will help you with that. Hopefully I've not missed anything out, and hopefully it wasn't too horrendous to follow.